Hi, I am Ryusuke Sugimoto from the University of Waterloo. In this video, I'll talk about our SIGGRAPH North America 2024 paper, Velocity-Based Monte Carlo Fluids. I worked on this project with my advisors, Christopher Batty and Toshiya Hachisuka. We present a velocity-based Monte Carlo fluid solver that can be readily extended with common techniques from the fluid animation literature, such as this buoyancy simulation. The previous application of Monte Carlo techniques to fluid simulation problems showed some promising advantages of Monte Carlo methods, such as the capability to solve problems with complex boundary geometry without relying on cut-cell or conforming mesh. This previous work employed a vorticity-based formulation. It is known that vorticity-based methods cannot correctly treat the harmonic velocity components as shown by Yin et al. When the vortex pair moves according to the velocity field induced by the vorticity, this colored smoke should flow in between the obstacles. Our method and the traditional velocity-based stable fluid method can correctly simulate that, but the previous vorticity-based Monte Carlo method fails to simulate this. Besides the problem of correctness under harmonic velocity components, velocity-based formulation has been the primary focus of the computer graphics community so far. So in addition to the viscosity simulation that the vorticity-based Monte Carlo method also supported, our method supports some velocity-based techniques including buoyancy simulation, divergence control, pick flip, and advection-reflection solver. Our starting point is the incompressible Navier-Stokes equations, following the standard velocity-based classical fluid animation framework. We apply the operator splitting method. We decompose the original Navier-Stokes equations into three equations and solve them one by one sequentially under a small time increment. For the advection step, we use the semi-Lagrangian advection. Consider updating the velocity value at point x. Assuming that we can query the velocity value u star there, we can estimate where this point is advected from. We then query the velocity value at that point and copy back to the original evaluation point x to update the velocity field. While using semi-Lagrangian advection is a very common technique, we emphasize here that this is a pointwise formulation. We can independently evaluate the updated velocity at any spatial point we are interested in, which is not necessarily aligned with, for example, a grid cell, assuming we can likewise query the velocity estimates from the previous step at any spatial point. When all the solvers for all substeps of the operator splitting method support this pointwise formulation, they offer greater flexibility in how we use these solvers. With this in mind, we will skip the diffusion step now and see the projection step next. The task here is to find the pressure gradient that removes the divergence in the input velocity field u star. It is equivalent to saying that the pressure must satisfy the Poisson equation given here. We try to convert this Poisson equation into integrals so we can use Monte Carlo integration techniques. Assuming there are no solid boundaries, with a fundamental solution of the Poisson equation g, we can express the pressure gradient as an integral over the infinite space. Because we cannot simulate everything inside of an unbounded domain, we assume that the divergence of the input velocity field is zero outside of a bounded simulation domain to make the integral domain bounded. Furthermore, we want to assume that we can query the velocity field itself and not the divergence of the velocity field as per the pointwise design we want to support. Therefore, we use integration by parts to remove the explicit dependency on the velocity divergence. To evaluate the pressure gradient at point x, first, we evaluate the first term by taking a weighted average of the contributions from sample points inside the fluid simulation domain. Similarly, we evaluate the second term using sample points on the boundary of the simulation domain. In the paper, we discuss how to deal with the problem of singular integral by combining importance sampling and control variance methods. Without using these techniques, the Monte Carlo estimate does not converge, so these are crucial to our method. At each evaluation point, using the estimated pressure gradient, we update the velocity. Note that this projection step solver is a pointwise solver too, where the evaluation point can be anywhere inside of the domain, assuming that we can query the input velocity anywhere. So that's how we solve the projection step when we do not have solid boundaries. When we do have solid boundaries, we get an additional integral term in the estimate when we work out the math. This additional integral contains the function mu, which encodes the effects of solid boundaries. However, to compute the function mu, we need to solve an integral equation. It might sound daunting at first, but this kind of integral equation is what Monte Carlo ray tracing techniques can nicely handle, and even for more general integral equations like the one we get for our problem, we can use a similar ray tracing style solver called the Wacom boundary method I presented last year at SIGGRAPH. We cast rays recursively to estimate the solution to the integral equation, and the result is used to compute the pressure gradient. That's how we solve the projection step. For the diffusion step, we similarly consider the case without solid boundaries first. In this case, we can solve the diffusion equation by applying a component-wise Gaussian blur to the input velocity field, and we can use Monte Carlo to evaluate this. When we do have solid boundaries, we use the Wacom boundary method. The diffusion equation is time-dependent, so instead of taking walks only on the spatial boundary, we need to take walks on the space-time domain. This diffusion step supports pointwise estimations too, and we discuss the details in the paper. With these three substep solvers, we can advance the velocity field for fluid simulation. Similar to traditional simulation techniques, we can use a discrete structure such as a grid to store the intermediate velocity field after each step. Even when we use a discrete structure, the solid boundaries are automatically handled with Wacom boundary without cut cell or conforming mesh. However, if we store the velocity field into a discrete structure, when we query the velocity from the discrete structure, it introduces interpolation errors. Remember that we have designed the solvers for all substeps to have the pointwise evaluation capability. Utilizing this property, we can remove some interpolation errors by querying the velocity on the fly whenever required by the next substep. This flexibility is a unique advantage that our Monte Carlo solver offers. In all of our implementations, we use a uniform grid structure or grid particle hybrid structure to store the intermediate velocity field at some point to avoid the growing computational cost, but there is much more to be explored beyond this option as our solvers are agnostic to the choice of discrete structure. Our implementation utilizes CUDA and optics, allowing us to take advantage of the algorithm's parallel nature and accelerate the ray intersection query. The first set of results shows the correctness of a viscous fluid simulation. As we change the Reynolds number, the simulation changes its turbulence as we expect. The next one is the application of the advection-reflection method to our framework, made possible by the velocity-based formulation. Compared to the one with advection projection, we get a more turbulent result. We can also replace the semi-Lagrangian advection step with a particle-based pick-flip advection to reduce numerical dissipation. The classic buoyancy and divergence control techniques were not applicable to the vorticity-based Monte Carlo method, but they are straightforward to implement within our framework. Besides the advantages that our method already demonstrates, there are a few open problems. In theory, utilizing the on-the-fly velocity query should reduce interpolation errors. While all three alternatives give consistent results with the traditional grid-based method, We do not see the clear advantage of using the on-the-fly evaluation with these examples. We are interested in the situations where this strategy offers greater advantages. Moreover, all the variants we show run magnitudes of order slower than the single-threaded CPU implementation of the traditional grid-based counterpart. Improvements in efficiency by, for example, utilizing the spatial and temporal coherence in the velocity field is an open problem. We presented the velocity-based solver for gas simulation in this work, and we look forward to the continued advancement of Monte Carlo techniques for problems with free surface and other physics simulations more broadly. To summarize, we presented a velocity-based Monte Carlo smoke simulator with operator splitting. We performed the projection step with a careful handling of velocity divergence. We extend the projection step for problems with solid boundaries using the Wacom boundary method. We apply the diffusion Wacom boundary method for the first time in computer graphics to solve the diffusion step. We successfully adopted many popular velocity-based techniques to our Monte Carlo method. Thank you very much for watching this video.